So let's derive the formula for relativistic mass. And this is one of several videos in which I do the same, get the same result, just doing it slightly differently. So I've an object that of mass m moving along at some velocity. So this would be the velocity of m. And in the S reference frame, it's equal to vi hat plus uj hat. And in the prime frame, which is moving along at some speed v, I have sort of a capital V here, is the velocity of s prime with respect to s in the I hat direction. And Vm prime is equal to V prime I hat plus U prime J hat. And just as a reminder, there's another video where I derived this, but the Lorentz transformation for a component of velocity perpendicular to the velocity of a reference frame would be U is equal to U prime over gamma 1 plus big V, which is the velocity of S prime frame with respect to S, times V prime divided by C squared, where gamma is the Lorentz factor for this reference frame S prime. I'm going to have two masses here, A and B, and I will make the assumption that the rest mass of A and the rest mass of B are equal to each other, and that's just going to be equal to m sub 0. So in the S frame, I have object A that's moving up. Object B is coming down at an angle at a speed uB. A and B will collide. B will then bounce up at an angle at a speed uB, and A will then bounce down at the speed ua. So A is originally moving upwards at a speed u0 in the j hat direction, and then it'll bounce back in the opposite direction at the same speed. So A doesn't change any kinetic energy, therefore, and B is not going to change any kinetic energy. Its final speed is equal to its initial speed. And in the second reference frame, B is actually just moving vertically, and A is the one that's moving, well, the opposite direction to what B was in the S frame. In the S prime frame, A is moving up and left, will collide with B and then move down and left. This is a perfectly elastic collision. In other words, energy is conserved. And as mentioned earlier, the initial speed of A is equal to the final speed of A. Initial speed of B is the final speed of B in either reference frame. So in the S frame, my VA initial is just U sub naught J hat, and VA final is negative U sub naught J hat. VB initial is UBX I hat minus UBY J hat, because again, I have I hat and J hat defined as such. And in the S frame, B is traveling initially down at that angle. So that's just going to be V I hat minus UBY J hat. So therefore, defining UBX as capital V. And so VB final would be big V I hat plus UBY J hat. Remember, big V is the velocity of S prime with respect to S. So in S prime frame, B is just going straight down and then straight back up. VB prime initial is negative UBY prime J hat, and then final would be UBY J hat. So it's initially going down, then going back up, which is just negative U naught J hat, which is just equal to U naught J hat. U prime BX is equal to 0. All right, so let's take a look at the relationship between the magnitude of UBY and UAY. We're going to do a Lorentz transformation for the perpendicular components of velocity, or components of the velocity of the masses that are perpendicular to the velocity of the prime frame with respect to S. So we have negative UBY is equal to UBY prime over gamma 1 plus big V U prime BX over C squared. And then U prime BX, again, we're in the prime frame. B is just moving down and up in the prime frame, and so this U prime BX is equal to 0. So this ultimately just becomes negative U sub naught over gamma, or negative U sub naught square root of 1 minus beta squared, which is V squared over C squared. Therefore, the magnitude of uby is less than the magnitude of u, because this term right here at most is 1, and at smallest it's 0, and so this fraction right here is going to be somewhere from 0 to 1, and therefore, looking at the beginning and ending of this trail of expressions, the magnitude of uby has to be less than or equal to u sub naught. And just one other point here. So uby would be equal to u sub naught only if big V right here is equal to 0. In other words, if S prime is not moving relative to S. And since uay is equal to u sub naught, coming back over here, ua is all in the y direction, and u sub naught is just that initial speed. They're equal to each other. Therefore, the magnitude uby is less than or equal to uay. In classical physics, I know that the total momentum in the j hat direction, initial is greater than 0. So looking in classical physics at the momentum, that mass times negative uby. Again, let's just take a look at here. We're in this reference frame right here. So ub we can break up into components. So I have ubx and uby. So mass of b times uby plus mass of a times uay, which would be the initial velocity going in that direction. Again, that's negative because this is the j hat equation. That would be equal to negative m sub naught times u naught times the square root of 1 minus big V squared over c squared, which we derived right up here, plus m sub naught u sub naught. Factor out m sub naught u sub naught, and we get 1 minus the square root of 1 minus big V squared over c squared, which is only going to be equal to 0 if V is equal to 0, this big V. In other words, if S prime and S are not moving relative to each other, but it is in this scenario because we set up the problem so that big V is bigger than 0. Afterwards, momentum is conserved. And you can go through the similar argument afterwards. This is positive and that's negative. Go through the same substitutions, you end up with a total momentum is less than 0. So if this is a pure classical physics problem, my total momentum beforehand the collision is bigger than 0 and less than 0 afterwards. P cannot be conserved because you would end up with, so P total y final, m sub naught u sub naught negative 1 plus the square root of 1 minus big V squared over c squared. And so since this, as long as big V is not 0, this term right here has to be less than 1, and so this total term has to be in between 0 and negative 1. In other words, it's negative. So we need to somehow resolve the issue. Looking at this from a classical physics point of view will not work. So let's resolve the issue and just assume that the mass is some function of velocity. Since since the speed of b in the j hat direction is less than the speed of a in the j hat direction, then if the speed of b is greater than the speed of a, then mb could be bigger than ma. And just point out, this is the speed in the j hat direction, and this is the total speed. So if ub has two components here, we have uby and then the horizontal component of v. So ub squared is uby squared plus ubx squared, and uby, as we resolved earlier, is just u sub naught square root of 1 minus big V squared over c squared plus v squared. Squaring this, we get u naught squared, and then the radical goes away. Distributing, we get this, and then factor out a v squared from these two terms, and we get u naught squared is equal to big V squared times 1 minus u naught squared over c squared. Sorry, this factor right here at most is 1, but it's not less than 0. This is a positive number. And therefore, this term right here is a positive number. Therefore, the whole thing must be bigger than u naught squared. So all of this is equal to ub squared, which is bigger than u naught squared, because this term is bigger than 0. And u naught squared is just uay squared. Therefore, ub squared is bigger than uay squared, or ub is bigger than ua. Because remember, in the S frame, a is just moving straight up. There is no x component, and so that is ua right there. All right, so ub is bigger than ua. And therefore, mb could be bigger than ma. Even though the rest masses are the same, the mass in the problem is not necessarily. So if we assume that mass is equal to some number times the rest mass, that they're directly proportional, and this z here is a function of the velocity, then mb would be zb m sub naught, and ma is za m sub naught. And we are also assuming that momentum is conserved. We still want momentum to be conserved, and our rationale for that is we're still using Newton's third law as a basis for it, that they exert equal magnitude of forces opposite directions. And since they exert the same magnitude of force for the same amount of time, the change in momentum on each must be equal in magnitude but opposite in direction. So this is the sort of a side note just justifying the fact that if Newton's third law is true, then momentum is conserved. The total momentum in the j-hat direction initially must be equal to the total momentum in the j-hat direction finally. So we have mb times negative uby plus ma uay is equal to mb uby plus ma negative uay. Again, we have b coming down like this, and then bouncing off like that, and a is just going up and down. So negative mb uby, just going ahead and multiplying through together to make it into slightly simpler format, bringing everything over to the right-hand side, and we have 0 is equal to 2 mb uby minus 2 ma uay, divide by 2, and then plug in our substitution, because remember we're saying that the masses of b and a are proportional to the initial mass based upon this conversion factor, which is speed dependent. And so zb m sub naught, that is this substitution right here, and uby, as we found on the previous page, is u naught square root of 1 minus big V squared over c squared minus za m sub naught, so that's this, u sub naught. So za, well, just basically divide by m sub naught, u sub naught. Those terms go away, and we're left with za. So that would give us, bringing that over to the other side, that gives us za is equal to zb square root of 1 minus big V squared over c squared. So za over the square root of 1 minus v squared over c squared is equal to zb. Well, that right there is just gamma. So zb is equal to za times gamma. So zb over za is equal to the Lorentz transformation factor. Pause it if you need to. All right, so gamma is equal to, well, 1 over the square root of 1 minus big V squared over c squared. I multiply top and bottom by this factor here. In the denominator, this gets, we're just basically doing FOIL. Get a common denominator for the, well, we have a common denominator here for this c squared. Do recognize that we do have a over c squared right there, just so that we have a common denominator. Factoring out big V, we get this. And this term right here, as we've done earlier, is just u sub b squared. So I have the square root of 1 minus u naught squared over c squared is the square root of 1 minus u sub b squared over c squared, which is just gamma u sub b over gamma u sub 0, which is zb over za. B was the initial speed of b, u naught is the initial speed of a in the S frame. So if we let z sub m equal gamma v sub m, in other words, this is the velocity that we're talking about in the formula, so this would be gamma is equal to 1 over the square root of 1 minus v sub m squared over c squared. So this works if we have z is equal to just gamma for that particular speed. So if we let z equal gamma, then m is Before, where we said m is equal to z times m sub naught, m would be just gamma times m sub naught for whatever the speed that that mass is going. And there is yet one more derivation.